Thank you very much. Pleasure to be here. Thank you for the time and also for your focus on the subject. Today we speak about energy, and let's see if this works. The subject is the future of energy, and the subtitle is what's Putin's cause in the current energy crisis we're actually facing. And I've been working on this subject for many years. It's sort of a private passion of mine. And what's currently happening in the world is quite a complex issue. So I'm trying today to give you a bit of a glimpse of the issues at hand, what the causes are, where we are today, and what the potential future might be. And some of what I say might be surprising to you. You may not have to agree with everything I say, but I hope it starts to open up your mind a little bit about this subject. Being in the financial markets, and many of you are, the subject of ESG has become very important. The environment is extremely important. And with the environment, often the discussion of energy comes because, energy seems to be the main cause of all the troubles we have with the environment. Generally, this new focus on the environment is very positive because we do need to realize that whatever we do in our life always has an impact on the environment. In fact, everything we do, and also in the future, it will have an impact on the environment. So when it comes to energy, we actually have three goals, right? We need to reduce or have the most energy with the least emissions, right? We need to have the most energy with the least effort. Actually, the energy efficiency needs to improve, needs to increase. That means we need to put as little input in to get the biggest output. And the third, actually, we need to improve the material efficiency. That means the raw material input for our energy we get needs to be reduced as much as possible. It actually started much earlier. Bloomberg had this interesting article last year in October and saying the global energy crisis is the first of many in the clean power era. I don't always agree with things that are written at Bloomberg, but this one I definitely agree with. So the situation really has become interesting, and my argument is actually what also the article said: the economy, the new economy, is overinvested, and the old economy is underinvested. I'll try to explain in today's discussion what I mean with that. This is supposed to show the primary energy supply for the past 200 years. And we can see that we are consuming whatever it is, 170,000 terawatt hours, a very big number. And that has increased with the Industrial Revolution started. Coal came first, oil age came, the gas age came. We started to develop the nuclear force, the nuclear energy came, right? In terms of our total energy supply today, 80% comes from fossil fuels, right? Oil, coal, and gas, in order of importance, are the current sources of our energy that we consume and that we supply in every way. Wind and solar, by the way, make up 3%. That hasn't changed in 2021. Now, what happens in the future, right? What happens in the next 30 years? And the argument is that actually we will need much more energy in the future. And that energy growth is driven by population increase and, of course, by energy per capita increase. As the poorer nations, as poor people become richer, they start to consume more energy. So both of these factors will probably mean that we'll likely have a 50%, maybe 40% increase in primary energy supply in the next 30 years. So where is this energy going to come from? And what's currently happening? The same 170,000 terawatt hours you see coal, gas and oil, and the importance of them. You have to understand energy is many things. Energy is, amongst others, of course, electricity that we use every day. It's also the heating, right? The heating our buildings and all those things. And then it's transportation, and then it's industry. So actually there's three main means for supply of energy. And when it comes to electricity, then coal and gas make up 60%, right? Indonesia is a large coal user and actually coal supplier to the world. This is important to keep in mind when we talk about the future of energy. Now, there's a lot of discussion about net zero and emissions and all those things. Actually, it's all about CO2. Actually, many of the discussions are. This is the IEA's net zero pathway, or what would have to happen to reach net zero in 2050. You would actually have to reduce primary energy by 10% in 8 years. That's a model that the IEA has. So whenever you hear net zero, there's some sort of pathway that goes with it. And all these pathways assume that we're gonna consume and produce much less energy than actually what we just discussed before. Secondly, they will assume that wind and solar will make up a significant, actually quite large, huge percentage of future energy supply. In this case, 40% in 25 or 28 years. So Germany today has 5%. Germany, the most advanced nation in terms of the energy transition, has reached 5% of its total energy supply from wind and solar. This just gives you a sense about something doesn't add up here. Okay? There is something what we call capacity factor. That means when you put up a windmill anywhere, that windmill will not always run, right? And that's independent of how modern this windmill is. When there's no wind, it doesn't run. Okay? And the average worldwide capacity factor is 21 to 24%. That means on average, that windmill will run 21 hours of 100 hours, or 21% of the year. And the rest of the time, there's just no wind. That's the average, worldwide average. Now in the north, where I am from, in Germany, and you have a lot of wind, you reach 35, 40%. In Indonesia, if you're lucky, you have 10%. In China, nothing. India, nothing. Africa, nothing. Vietnam, a little bit. Japan, a little bit. Now, being with financial people and return on investment you're very familiar with, hopefully you put $1 in, you get $2 out, and hopefully you do that in a couple of years, not too long, right, in the future. So the same concept exists for energy, and that's called energy return on investment, right? So when you create energy, you need to actually first do work to get that energy. You need to build a power plant, you need to mine coal, you need to build a solar panel, whatever. You need to do something before you actually get the energy out. And that's an energy input. And as with money, you hope to put the least in to get the most out. Very simple. Now, the EROI, the energy return on investment, actually is energy efficiency. That measures the net energy efficiency. That's what we need to improve, maximize at all costs. Because only when we become more efficient in our energy generation will we actually do something good for the environment. Only then. Today, the most energy efficient way of producing energy is nuclear. Nuclear probably has an EROI of maybe 70 to 80 times. That means you put 1 unit of energy in to produce uranium, to build the power plant, all those things, and you get 80 units of energy out for each one you put in. That's very efficient. Wow. Second most best is probably hydro. Hydro, you put in 1 unit in and you get maybe 40 units out, 35 units out. The numbers are not very exact because the science on this is not very developed. I'm writing a paper on this, but it's difficult to really get the exact numbers. But this is more conceptually to get the point across. The third one is actually thermal, coal and gas, right? The way to thermal, like combust fossil fuels, get energy out. It's a very energy efficient way of doing it, less efficient than nuclear, actually less efficient than hydro. So why are we not doing more nuclear? Well, because it's more expensive. Right? So in fact, coal and gas is the least expensive way of producing energy. So it's like an optimal path, get the highest efficiency with the least input, not only energy, but also money. But remember, this graph only shows energy efficiency. Up there is the cost. And I'm showing the full cost of electricity. I'm not showing the marginal cost of electricity. Very important. Now, interestingly enough, when you go to wind, solar, and biomass, you actually have a very low energy efficiency. An extremely low energy efficiency. It's actually the most expensive. Full cost of electricity, not marginal cost of electricity. Okay. Now, what's even more important or interesting is that our society today requires a minimum energy efficiency to actually sustain itself. We wouldn't be sitting here, we wouldn't have universities, we wouldn't have hospitals if we didn't have a certain minimum energy efficiency, right? Like we cannot go back to, like a 2 to 1. In fact, the Romans had 2 to 1. The Romans were the most advanced society prior to the Industrial Revolution. They had a 2 to 1 energy efficiency. Roman cities could only reach a certain size because the energy efficiency didn't allow bigger cities. And only when the Industrial Revolution came, when we developed the power of coal, could we actually do what we do today, start doing what we do today. Now, of course, technology will improve these efficiencies over time, all of them, right? So we're going to develop on all of these to get them better. But if the world were today go 100% wind, solar, and biomass, we would not be sitting here. There would not be enough energy. We would go into energy starvation, and that's what you start to see now in the market. The second environmental fact that we discussed previously, is the material input. Remember, we want to also have the least raw material input per energy output. The least tons of materials to produce the energy. And it turns out that nuclear and coal and gas have the highest material efficiency in tons input per energy output, not about money, not about emissions, it's about just tons, okay? And hydro and solar, wind, biomass have the highest or the lowest efficiency and the highest material input. And then the next is the space requirement. The space requirement is becoming very important. The space required for hydro is much higher than for a coal or gas power plant, right? For hydro, you need to, affect rivers, put large walls up. It takes much more space. And wind, solar, and biomass, naturally, because of the energy density, it's very low energy density, you need to have huge space required. These are also environmental measures. And when you don't believe this material input, this is from the Department of Energy in the US, which just shows the materials in tons per terawatt hour capacity: coal, gas, nuclear, hydro, solar, wind, geothermal. Now, this is a little bit old, the numbers probably changed today, but just gives you a sense that the materials required to put up energy systems make a difference. Also for electric vehicles, by the way. Also for electric vehicles. Electric vehicles are not producing energy. Electric vehicles are consuming energy. I'm talking about the production of energy, not the consumption of energy. Now, when you start to capture carbon dioxide from coal and gas, you will what? Reduce the energy efficiency, because it takes energy to capture the carbon dioxide. CCUS reduces the energy efficiency. When you start to produce hydrogen from wind and solar, you do what? You reduce the energy efficiency, because you need to have more energy to produce the hydrogen. Hydrogen doesn't come from the ground. Hydrogen needs to be produced. It needs energy. In fact, you lose 60% of the hydrogen, of the energy producing hydrogen. 60%. And by the way, you would only use excess, unutilized renewables to produce hydrogen. Why? Well, because if I have wind or solar energy coming out of my socket, I charge my Tesla directly first, before I make hydrogen, and then charge my Tesla afterwards. But why would I first produce hydrogen and then charge my Tesla? No, I first charge my Tesla until my Tesla is charged. And only the excess unutilized renewable energy I would use to produce hydrogen. And this is what happened to the, again, I apologize for the formatting. This is what happens with the installed power capacity in Germany. Germany's power capacity has doubled in the past 20 years. From 115 gigawatt to 222 gigawatt, it has doubled. In fact, the fossil fuel capacity increased from 75 gigawatt to 79 gigawatt. Indonesia has, I think, 85 or 90 gigawatt. So just like that fossil fuel capacity, that would power all of Indonesia today. Nuclear reduced, and wind and solar went up, shot up. But actually, we just doubled our electricity system. Now with that, we were able to produce electricity only 30% from wind and solar. So this doubling in capacity produced 30% of electricity, and actually 5% of total primary energy. By the way, the worldwide capacity is 8,000 gigawatt, 8 terawatt hours. Sorry, terawatt, not terawatt hours. 8 terawatt of total globally installed capacity of everything. Now, what the world is doing is, in 2019, we're at 1.5 terawatt of wind and solar alone. And in March this year, just last month, we reached 1 terawatt solar. You saw it maybe in the press. We reached 1 terawatt of solar installed. Wow, great news. Energy transition is going away. We are producing more from solar and wind and all those things. Now, the pathways are such that within 8 years, we are supposed to build 8.6 terawatt of wind and solar. This comes from BCG, my own company. I used to work there for 7 years. 8.7 terawatt are supposed to be built in the next 8 years of wind and solar. That means we're going to double our existing infrastructure. We're going to double it. On top, put the same capacity of wind and solar up, which is actually the least energy efficient because of the space requirement, material input, and all those things. By 2040, we're going to have double again. And by 2050, we're going to put another 7-8 terawatt on top. That is the current pathway we are going. And I am asking, how is this environmentally friendly? When we look at the environmental impact of our energy systems, we have to look at the entire value chain. There's a production of raw materials that we have to consider. There's processing of raw materials that we have to consider. There's transportation of raw materials and products that have to consider. Of course, there's the actual operation, the combustion of materials, whatever we do, the production. And then, of course, there's the recycling. So these are the main steps where we have to consider our environmental impact. Emissions included that, and then there's non-emissions, right? Because environmental is not only emissions, there's many other issues we just discussed, right? And greenhouse gases are some of the emissions which we have to consider, but then there's many other emissions we have to consider as well. Sulfur oxide, nitrogen oxides, right? Mercury, chlorine, particulate matter, right? All those things, these are all emissions, right? And then there's the non-emissions, the energy efficiency, the material efficiency, right? The space requirement, the waste requirement, the effect on animal and plant life, effect on health and safety. All these issues are environmental issues we have to consider. And what are we doing? The current focus on energy policy is all about operation and combustion only. We are only measuring the CO2 from combustion. Wind and solar have zero CO2. Why? Because during combustion they don't produce CO2. But when you look at the entire value chain, they produce a lot of CO2. Probably still less than coal. Coal produces double the CO2 that gas does. So we're switching from coal to LNG to gas in Asia to try to save the climate or to help to reduce the climate. In fact, when you consider the value chain, when you consider methane, it turns out that coal is better than LNG for the climate. I just wrote a paper on this, it just got published, peer-reviewed. which proves without beyond doubt that actually coal is better for the climate than LNG. This just gives you a sense of that current carbon taxation actually leads to distortion and undesired consequences. Because we are not having a macro view of what is happening worldwide. We're starting to focus on one thing only and only one thing. And if you were to look at everything together, then we can make a positive difference to our life. In everything. Now, we have made a positive difference to our life already. This is the life expectancy over the past 500 years. With the Industrial Revolution, we were able to double our life expectancy because access to energy gives life, length of life, health, safety. Energy is the basis of this. We have reached this, we have managed this. This is extremely positive news. Poverty has gone down to levels we've never seen. It's still there, but it has gone down to levels we've never seen. The first thing, in my humble opinion, my first recommendation would be to invest in base research to sustainably wean off fossil fuels. Because we can't forever dig things out of the ground and burn them. Right now, that seems to be the best we have, but we can't do that forever. We have enough resources, but not forever, ever, like for 1,000 years maybe, but not for like 20,000 years, right? So we have to invest in research to find a solution to our energy problem, right? Energy generation, material extraction, processing, storage, superconductors, all these things need to be researched because obviously we don't have a solution yet, as we just showed before. Now, what the solution will be, it will be a combination probably of the nuclear force, fusion, fission, we don't know yet. It will be the power of our planetary system. There's so much energy in our planetary system, including the sun, that we need to harness, including the power of the sun. But photovoltaic is not the solution because it's energy inefficient at large scale. Doesn't mean every solar panel is bad, but if you try to replace your entire system with solar, you go in energy starvation. You don't have enough energy to build the solar panels. And the third is probably the energy from within our planet. There's so much energy within our planet. I'm just talking about geothermal as one example. There's so much energy down there, we can need to find that. We don't have the solution yet. But my sense is that these three things we need to invest in to find the solution. By the way, we also have to understand that, remember the first law of energy, thermodynamics, that energy is never lost. So what happens with all the energy we produce and we consume? Where does it go? It is never lost. All the energy, the car, the industries, AC, air conditioning, everything ends up in heat. Where does the heat go? Into the biosphere, up there, into space. Right here, you have Milan in the summer of 2019. You see the temperatures in the city are 4 degrees warmer than outside the city. So of course we're warming our planet. Huge amount of energies all ends up in our biosphere. It's called the urban heat island effect. Now, the second thing we have to do is we actually have to invest in our existing infrastructure to reduce the environmental burden and to increase the energy efficiency. We need to invest in what we have to make it better, right? Reduce the waste we generate, waste to power. And actually, energy, as we learned, reduces poverty. And when you're richer, you can also handle, bad weather better. So instead of divestment, what do we have to do? Investment. So in summary, right, there's a fundamental underinvestment of the old economy, and there's far too much money going to the new economy. I'm all for investment, but logical investment. And trying to replace our existing infrastructure with wind, solar, and biomass, we are going into energy starvation, which we are starting to see now. You will have blackouts in Europe, not caused by Putin. The entire supply chain counts, right? The current sole focus on combustion and operations only distorts and is costly. Example, LNG is better for the climate than coal, because we have to look at the supply chain. Emissions are only part of the problem. The non-emission material input, energy input, space requirement, recycling are at least, if not more important for the environment. The current energy crisis is caused by underinvestment in reliable energy systems. And if Asia continues the path of the West, this will also hit Asia. Thank you.